Hello everyone. Today we're diving into high performance compute, HPC as they call it, and its role in drones and robotics. Now, whether it's training AI, simulating complex flight scenarios of a drone, or enabling real-time operations, now HPC is the backbone of most of the cutting-edge drone technology. Now, I'll share resources to get you started with HPC, and my plan is to use these HPC concepts in embedded devices like the TDA4VM from Texas Instruments. There are many embedded devices like the NXP i.MX8, the NVIDIA Jetsons, but in this particular case, I'll be using the TDA4VM. And I want to tackle some of the common misconception that if you throw more hardware at a problem, it technically does not guarantee success. Now, it's nice to throw more hardware, but understanding how the hardware works and squeezing every juice out of those computes is an important skill set. So let's dive in. Now, what is HPC and why does it even matter? Now, HPC stands for high performance computing. It's all about solving these massive computational problems and quickly leveraging. For example, in the TDA4VM, we have heterogeneous computing. We have, the core A7s. We have we have DSPs. We have the MCU islands. So there's a lot of just different types of compute just on this particular device. How do we leverage all of it in a real-time setting? So that's kind of like heterogeneous computing. But heterogeneous computing could also mean combining CPUs and GPUs, accelerators, FPGAs for specialized tasks. Another thing that when you have multiple computers or heterogeneous computing, inside each of these computes, there's parallelism that you could leverage. And parallelism is a big part of squeezing out every ounce and juice from your hardware. So it's breaking these tasks into smaller operations that can be computed simultaneously. We also have distributed computing when you have a cluster of all of these systems, and you can use these clusters to handle computation across multiple machines. There are many optimization frameworks such as OpenMP, MPI, single instruction multiple data, single instruction multiple thread, very specific to the hardware that you're working with, that you can maximize the performance and squeeze as much juice from your hardware. There's one misconception though, and I won't say misconception, but kind of like it's all about having faster hardware, and it's all about having throwing more hardware at a problem. So HPC isn't just about having fast hardware, it's also about understanding how to utilize the hardware, and that understanding is really a philosophy, and that's really kind of what I'm trying to the message that I'm trying to send over here. Now, there's a common misconception or common notion in AI training that let's get a bunch of GPUs and it'll train faster. Now, as I mentioned earlier, while hardware is essential, just throwing hardware at the problem is not be all end all kind of a thing. It's not going to solve it, and the reason being is because you really need to understand how compute works. And even if you throw in and spend all your money on these high-end hardware, if you don't know how to utilize it from a fundamental level and you're just relying on abstractions, most likely you're not going to make the most out of it. So training faster isn't just about adding GPUs. It's about optimizing how data flows and how task is distributed. So if you understand your memory hierarchy and the compute, there are all of these small little optimizations that over time, where every single improvement makes a difference. Understanding where the bottleneck is at the deeper level can help you get more out of your hardware. So tools like CUDA and OpenCL provide low-level control over your GPUs. But without understanding these tools, even the high-end hardware won't perform optimally. You could literally write a bunch of for loops, on one single thread on a CPU with a multi-core system, and you're leveraging all the cores that's in there. That's a good example of just throwing hardware is not going to solve the problem. And another point that I want to kind of like, harp on is that abstractions, they are nice. Now, I come from, at this point in time, I'm working a lot with, web development, and over the last 9 to 10 years, abstractions has literally made web development lives easier. You don't go and design your own database. You don't go and design your own, Linux, system. Docker takes care of all of those things. Databases are now kind of taking care of all of those things. Now you have infrastructure as code that takes care of, all the CI/CD pipeline. So you're building over abstractions, over abstractions, over abstractions. For a matter of fact, it's just a matter of, my front-end web development. I'm going to use, things like Vue or, React. Backend, I'm going to use a framework, and it's all abstracted to a point where all you need to know is, how to use those abstractions. But as you and for the most part, even the slowest computer, modern day slow computer, is still very much capable of handling all of those tasks. We're not talking about, a computer that's 20 years old, but if you buy even, the cheapest and computer today, it'll handle all these web development tasks. So hardware and optimization and speed is not a factor in web development for the most part, especially, as a consumer, or if you're doing with client side things. Unless you're dealing with, the infrastructure of very, very high scale, which very few companies, you can count on your fingers, who are dealing with those types of scale. For the most part, abstractions was your friend, and it's still your friend. Don't get me wrong, but they have limits. So similarly in AI, especially with now the advances of AI and leveraging all of these capabilities, and you want to put them in your drone, frameworks like TensorFlow and PyTorch are great, but they also do abstract many critical performance details. So they're great to, get something training very quickly, but, these abstractions may not fully utilize your hardware unless you understand the fundamentals. So learning the fundamental is key, and HPC as a concept, as a philosophy, kinds of nudges you in the direction of, understand, what's happening under the hood. So now, knowing how HPC concepts work, like memory alignment, data locality, parallelism, work, you kind of understand, how to get the most out of your hardware. And a deeper understanding, just make sure, that your system scales efficiently as you had resources. So if you can optimize for one particular hardware, the more you grow, and that those optimizations, you're squeezing every single ounce of compute from that hardware, and it can be very specific depending on your GPU, depending on your accelerator, depending on your on the make and the manufacturer. But if you know how to squeeze all of those details from your compute, you can you'll save money, you'll save time, and you can get the most out of it. So the takeaway that I want to really emphasize is that more hardware isn't always better. Try to make your hardware work smarter and not harder, especially when you come with things like embedded systems, where they have tremendous capabilities in here, and there's a lot of heterogeneous computing that's happening in this small little edge device. Understanding these things can help you get the most out of it. So now the next thing that I want to talk about is how HPC, drones, and robotics kind of fits this equation. So now HPC isn't just about supercomputers and doing these things offline. It's also becoming extremely relevant for enabling drone technology. So one of the things you can talk about is fast AI training. HPC clusters can train neural networks faster, optimizing models for navigation and detection. That's why you would use, the AI model in your embedded systems. Simulation and testing. Now, simulating a real-world condition like weather, turbulence, and control dynamics reduces hardware iterations. Real-time inference. Now, onboard HPC concepts, like those that you can see on the TDA4 VM, you can enable things like sensor fusion, obstacle detection on the edge. Like these hardwares are capable of doing many, many things, including not just real-time flight control, but also advanced navigation, inferencing things from an AI to do things like object detection, depth detection, path navigation. You need to know how to squeeze every single ounce, from this compute, which I'll be talking about in future videos. If you're interested, please do comment below if you want to know more about, how to leverage heterogeneous computing in devices like these. And you can also use them for swarm coordination, where you can have external HPC clusters manage, a fleet of drones, and so that they can have synchronized operations in complex missions. So you'll have kind of like a mother a mothership, kind of a thing, and that's kind of sending signals to these drones so that they can perform things like navigation, surveillance, monitoring, search and rescue over a larger terrain. Now, the TDA4 VM is a great example of how HPC principles can be applied to embedded systems. So this is an example where I'm really talking about how you can use HPC. As I mentioned earlier, it's got a heterogeneous architecture, so it combines ARM Cortex cores, DSPs, accelerators for tasks like AI inference and vision processing. You can also use onboard optimization using frameworks like TensorRT, and I personally plan to optimize AI models for real-time decisions directly on this device over time. You can also do hybrid computing by offloading heavy tasks to external HPC systems and executing the lightweight ones on the TDA4 VM. As I mentioned, the drone orchestration can be done on an offload system, but on board you can do things like object detection, depth detection, crash detection, while doing all the attitude control of your flight control systems. So my goal is to kind of use this as a platform to exercise a lot of the high performance concepts on an edge device. So how do you get started with HPC concepts? So step one, let's understand the basics. My goal and my intention is that if you could understand things like learn parallel programming and concepts like multi-threading, single instruction multiple data like SIMD, distributed computing, that can truly help you understand the core concepts of high performance compute. And there are many books that I could recommend. I've just glimpsed through this. One of them is Introduction to Parallel Computing by Anand Grama, and then there's High Performance Computing Systems, Modern Systems and Practices by Thomas Sterling. There are also courses by NVIDIA on deep learning institutes, and even the Intel's HPC developer platform. You can go on the Intel's Tiber platform and you can play around with all of the notebooks to leverage some of the HPC concepts. So go out there. There are a lot of resources on understanding how to use HPC. The second one I would, there's no shortcut to this, which is you have to experiment with code, which means you have to technically go and program. You gotta go and make this physically go and experiment with all of these concepts. So you can use tools like MPI, message passing interface, for distributed systems, OpenMP for shared memory parallelism, and start by small parallelizing loops in your existing code and frameworks, and utilize your OpenMP and see the speed difference. So for example, if you have a simple for loop that's adding a number, or converting a uppercase text to a lowercase text across multiple documents, and you have this for loop, try using OpenMP to parallelize across the cores on your system and see how that works, and you can see the speed difference. I could even try OpenMP on this particular platform, by the way. So believe it or not, you can do parallelism because it's running a Linux system, Linux computer on this. The two A72 cores that's there on the TDA4 VM. Texas Instrument also has the AM69A, which I might experiment with. That's more of a general purpose edge AI solution. This is more of a hybrid because it has MCU islands. So there's subtle differences between a device that has some very high real-time capabilities versus the more general purpose edge AI computing system. So this is more I think more relevant to the kind of work that I want to do. But you can leverage all of these concepts and practice them on a device like this. And there's also NVIDIA Jetson, there's the i.MX from NXP. So there's a lot of manufacturers creating edge computing devices to leverage HPC concepts. You could also try HPC services on the cloud. So services like the Intel Dev Cloud, which is the Intel Tiber platform, they provide kind of free access to their HPC clusters with a lot of Jupyter notebooks, making it easy to you to experiment with kind of expensive hardware that you don't have to buy. There's also other cloud platforms like AWS, I think, has their own HPC instances. So does Microsoft Azure, and even Google Cloud with their TPU instance, which you can use in the Google Colab environment and enable some of their TPUs. So the next thing that I want to talk about is how do you incorporate HPC in drone development. So one of the main core things when it comes to AI and doing all this navigation and depth detection and obstacle avoidance is that you need to have this model already pre-trained with all of this information, so that when you're deploying it onto a real-time system, it's able to just do the inference, and you're not really training it on the edge. So HPC concepts will help you with simulation and AI training. So when you use cloud, like you can use the cloud platforms to train the AI models on a very large data sets, and you'll also be using the HPC concepts in terms of like designing and working with flight dynamics. Tools like ANSYS and MATLAB, they also have capabilities of leveraging HPC to give you faster results. So you can have the opportunity, by understanding these concepts, you can utilize these tools to leverage more of the hardware, because now you can speed up the simulation, or do something that's more complex than something that's very simple, because you know how to utilize the hardware. Another thing is onboard real-time processing. So if you deploy a trained AI models on the edge devices, for example on the TDA4VM, the NVIDIA Jetson, or the i.MX8 by NXP, and if you utilize frameworks like TensorRT, the OpenVINO, Vino, however you want to pronounce it, and if your model is optimized for inference, then you can optimize these models for onboard HPC inference, basically. And last but not least is swarm coordination. If you have multiple robots and drones and you want to coordinate them, if you implement a hybrid system where you have an external HPC cluster and you want to compute these global swarm behaviors, while drones process these local decisions on board. So that's the kind of like applications you can work with when it comes to drone technology. So why do you want to learn the HPC fundamentals? What's the purpose of this? So this is where it truly it kind of like rubs me the wrong way when many people come up to me and say like, why we just use abstractions? Why do you need to learn what's in the abstraction? And if that's the kind of attitude you have, that's fine. No harm taken. But I think understanding how abstractions work is a very important thing. It, I think, just pays dividends in the long run. So tools like TensorFlow and PyTorch, though they simplify AI development, learning how the compute works at a lower level just helps you, just helps your code to be scalable and efficient. It kind of helps you, debug and optimize performance bottlenecks. It empowers you. That's really it. It empowers you to design systems that are tailored to your specific workload. And empowerment, enlightenment, it's all just a good feeling. And my hunch is that if you understand the HPC fundamentals in the long term, these investments they will help you both in your skills and in creating successful projects. So that's the reason why I'm promoting a lot of the HPC concepts, because it's more of a philosophy of unraveling the abstractions. That's really it. So in conclusion, HPC is the key to unlocking the next generations of drones and robotics. Whether you like it or not, with the advent of AI, understanding and the amount of compute resources that these AI models need, and when you give them that kind of compute resources, they become so much more capable. Understanding how to squeeze every ounce of and juice from those compute will only help and make your models not only run faster, but also be better. So that's where the future is. So whether you're simulating flight dynamics, whether you're training an AI or deploying real-time solution, the concepts of HPC will provide you the computational backbone needed for you to take advantage of all of these applications and systems. So start small, use accessible resources, and you don't need to break the bank learning how HPC works, though it might have that misconception that you need supercomputers to get started. That's it for today. And if you really like this video, and if you want me to explore more about TDA4VMs or any heterogeneous computing platforms or edge platforms, do comment below. I am planning to make a lot more videos on leveraging high performance capabilities using these types of devices. And if it's something that's interested to you, please do comment. Or if you have another edge device that you would like to know more about and how to squeeze every performance from it, do comment below. So until next time, thank you.